Welcome back. Today, we're jumping into a real classic from Irodov's legendary problem book, number 1.76. Now, this one looks pretty innocent at first, just a couple of masses and a pulley. But trust me, it has a clever twist that trips up a lot of students. So we're going to take it apart piece by piece and really see what's going on under the hood.
Okay, so here's the deal. We've got two bodies connected by a thread. Body 1 is the heavier one, so it's going to fall. And as it falls, it's going to pull body 2 up. The question seems simple enough, right? How high does body 2 actually go? But like the slide says, the answer is probably a bit further than your first guess, and it's all because of that clever movable pulley.
All right, let's get the details straight. We're told that mass 1 is exactly 4 times heavier than mass 2, and we know that mass 1 starts 20 centimeters off the floor. Our job, our mission, is to figure out the absolute maximum height that body 2 reaches. So let's start building our solution.
Now, there are a couple of ways we can crack this nut. We're going to start with the most fundamental approach, the force method. We'll use Newton's laws to build a really complete picture of what's happening moment by moment. It's the long way, sure, but it's great for making sure we don't miss a single detail.
Okay, this right here, this is the first big hurdle, what we call the kinematic constraint, and it's probably the most common place to get stuck. Just think about the string for a second. If body 1 drops by, say, 10 centimeters, where does that 10 centimeters of string come from? Well, it has to be pulled from the section holding up body 2, but since there are 2 strands holding up body 2, each strand only needs to give up 5 centimeters. So body 2 only moves up half the distance. And that means its acceleration a2 is going to be half of a1. Getting this relationship right is absolutely everything.
So next up, let's get our forces straight. For body 1, it's pretty simple. It's just a tug of war between gravity pulling it down and the tension in the rope, T, pulling it up. But for body 2, well, it's a little different. Gravity is pulling it down, sure, but it's being held up by 2 strands of that same rope. So the total upward force on it is double the tension. It's 2T. That's another key detail you just can't miss. Now we translate those force diagrams into math using our old friend F equals ma. For body 1, which is moving down, the net force is its weight minus the tension. For body 2, which is moving up, the net force is that upward pull of 2T minus its weight. And look closely. See what we did there in the first equation? We've already plugged in our kinematic constraint, A1 equals 2A2. That's the secret key that's going to let us solve this whole system.
So now we've got 2 equations and 2 things we don't know, the tension T and the acceleration A2. The game plan is to combine them. We can rearrange one equation to solve for T and then plug that expression into the other equation. It lets us completely eliminate the tension and solve directly for the acceleration of body 2, which is exactly what we need right now.
And after we do a little bit of algebra and plug in that m1 equals 4m2, this is what we get. The acceleration of body 2 is 7g divided by 17. To put that into perspective, that's a little less than half the acceleration of gravity. So yeah, it's moving up, but not super fast.
So, why did we need that acceleration? Well, we need it to find out how fast body 2 is moving at one very specific moment, the exact instant that body 1 hits the floor. We know body 1 falls 20 centimeters, which means body 2 has only risen 10 centimeters. We've got the acceleration, we've got the distance, so we can use a standard kinematic equation to find its velocity at that point.
Okay, so body 2 has gone up 10 centimeters. We know its velocity. You might be thinking, great, we're done, but are we really? Is that the maximum height? Not even close. And this is the part of the problem that's so cool. The second body 1 smacks into the ground, what happens to the rope? It goes completely slack. All that tension just vanishes. But body 2, it's still moving upwards. It's basically just been launched. It's now a projectile.
And that brings us to Act 2 of this little physics drama, the free fall. Body 2 is now on its own. It's just like a ball you've tossed straight up into the air. It's got an initial upward speed, and the only thing acting on it now is good old gravity.
Yep, the tension is gone. So it's just body 2 fighting against gravity. It's going to keep rising, of course, but it's slowing down every single moment as its kinetic energy, the energy of motion, gets converted into potential energy, the energy of height.
And here's the beautiful connection between the 2 parts of the problem. That final velocity from phase 1, that becomes the initial velocity for phase 2. So we can take that speed we calculated earlier, plug it into another kinematic equation, and figure out exactly how much more height it's going to gain before it finally comes to a stop.
Okay, so that was the force method. It works. It's solid. It gets you the answer. But, for problems like this, there's often a much more elegant way. A shortcut, really. Let's rewind and see how we can use the conservation of energy to get to the same point with a lot less fuss.
The energy method is beautiful because it doesn't care about the forces or accelerations along the way. It just looks at the beginning and the end. You can think of it like an energy bank account. The potential energy that body 1 loses by falling down doesn't just vanish. That energy gets spent on two things, giving both masses some kinetic energy and giving body 2 some extra potential energy as it rises. The total energy never changes.
And as you can see here, it doesn't matter which path you take. Both methods get you to the exact same destination, the same velocity for body 2 right before the rope goes slack. The energy method can be way faster because you just write one equation and solve. It's also a fantastic way to double-check your work if you use the force method first.
So we've solved it two different ways. Now let's just zoom out and boil it all down. What are the most important lessons here, and what are the common traps you need to watch out for? These are the classic mistakes I see all the time. First, messing up the setup. Forgetting that A1 is 2A2 or that the upward force on body 2 is 2T will send you down the wrong path from the start. Also, mixing up the distances. Remember, body 2 only moves h/2 while they're connected. But the biggest trap of all is stopping too early. You have to remember that second phase, the freefall. If you forget that, you'll never get the right answer. So, to get our final grand total height, we just add the two pieces together. We take the height it gained in phase 1, which was h-half, and we add the extra height it coasted upwards in phase 2. And when you do all the math, it simplifies down to this really clean, elegant expression. The maximum height is just 12 times h divided by 17.
And now for the big reveal. We plug in our starting height, h equals 20 centimeters, and we find that the maximum height body 2 reaches is about 14.1 centimeters. Remember, it only went up 10 centimeters in the first part. That extra 4.1 centimeters all came from that crucial second phase of freefall motion.
So that leaves us with one last thought. Which way felt better to you? The step-by-step methodical logic of the force method or the big-picture elegant approach of conservation of energy? There's no right answer, of course, but becoming a really strong problem solver means having both of those tools in your toolbox and knowing which one to pull out for the job.